So Colin is Managing Director and Chief Scientist at QROS. He's qualified chemist with over 20 years experience of contaminated land analysis, both in traditional fixed-based laboratories and as the developer of many on-site analytical techniques. So today, Colin will discuss how getting accreditation for mobile methods is becoming overcome by UKAS accreditation of static units and the support they are getting from the Environment Agency. So as always, there's going to be time for a Q&A session after Colin's presentation. So do submit your questions in the chat box in the bottom left-hand corner of your screen at any point during the webinar, and these will be asked on your behalf at the end. So thank you for logging in, and Colin, it's over to you.
Okay, thanks, Rhiannon, and good afternoon, everyone. Thank you for taking time out your lunch. Okay, so yeah, I'm going to talk about on-site analysis and particularly the petroleum hydrocarbon analysis and all the fun that you can have with that. But first of all, I'd just like to give a sort of more of a background introduction to chemical analysis, or the sort of chemical analysis that we need for our profession, that is the environmental site investigation and remediation. So, chemical analysis. Most commonly analysed chemicals for soil and water are total petroleum hydrocarbons, and that includes the BTEXs, polyaromatic hydrocarbons, that's both as 16 or 17 or 18, depending on which legislation you want to look at, the individual compounds, and total aromatics. There's heavy metals. There should really be asbestos in there, but that's the subject of an entirely different lecture. A lot of controversy over it. Basically, if you can see you've got asbestos bits, you've got an asbestos problem. If you don't see asbestos bits, you probably haven't, because there's asbestos in everything if you look hard enough. Okay, that little set there is all that's required to identify and manage contamination about 90% of all your projects, and it's the TPH, PAH, and BTEX which are the most frequently required, followed by heavy metals. So how's data used? Well, for SIs, it's used to identify the contaminant type. Is diesel, is it coal tar, is it lead, chrome, organic pollutants, and I seem to have lost it. Ah, there we go, we're back again. To find out where the contaminants are on the site and to identify the concentration ranges of those contaminants. Now, with high precision analysis, you can look at target compounds. And this data is used in risk assessment models. So you want really accurate specific concentration values for certain chemicals such as benzene or benzopyrene or tetrachloroethane. And that includes the heavy metals. And if you've got a result that says we've got quite a lot of chrome, well, what chrome? If it's chrome 3, it's not a problem, but if it's chrome 6, it is a problem. And so you do actually need to know oxidation states. It's the same with arsenic. Arsenic 3 or arsenic 5 have different toxicity profiles, and this is needed for reliable and accurate risk assessment. And so if you're looking at remediation, you're really looking to check what the contaminant type and concentration is for WM3 hazard classification of your stockpiles, and to confirm if the contamination has been removed or if your treatment program is working effectively. That is bioremediation or soil washing, etc., etc. So you don't really need the data for much more than that, really. Now, coming back to the site investigation, if too few samples are analysed across the site, statistical significance and reliability of your CSM is not going to be very good. The consequences of that are the remediation strategy recommends treatment or removal of uncontaminated soil and water. That's expensive, it's wasteful, and it will increase the time and the costs to complete the project. So if you are putting together a proposal, you'll estimate it to be much higher than it should be, and you could potentially lose the job to another contractor. Or you just basically end up being completely overrunning your budget and not getting paid, so you make a loss. For when it comes to remediation, again, too few samples are analysed, so your CSM's wrong, and you end up pulling up unexpected contamination. And that is going to add extra problems, but especially if you're disposing of it with an incorrect hazard classification, because under new rules from April of this year, can lead to substantial fines, costs, potential prosecution. So not detecting contamination is costly and could give you the criminal conviction. And if you're the liable person, that could be you. So something to be aware of. So let's just have a quick look at that in real terms. Fairly typical site, well, not typical because I've just squared it up a bit, but a 75-meter area, an underground storage tank. Let's just sample it and find out if it has got contamination. Standard 25-meter grid, 15 sampling points. So the samples have gone off. A couple of weeks later, they come back, and you can see that we have two hot spots. A, which is above 10,000 milligrams per kilogram, and B, below 10,000 milligrams per kilogram, and the rest, well, it's below 100, so nobody's particularly bothered. So what is the remediation strategy for that? Well, we will cut out the so that those areas that are in the pink, they are four sectors there, and all going as hazardous, and the 3 blue ones as non-hazardous. Total loads, 109 hazardous loads and 80 non-hazardous. Well, job done though, all the contamination's gone, everyone happy. However, what if we did it a different way? Here, we've actually, same site, but now it's a 12.5 meter grid, so you only just halve the grid size. And you use iterative sampling using the on-site methods. And unfortunately, because of the way this presentation works, you can't see the progress, but basically, you've identified now 4 hotspots, and you've worked in real time around each time you find a hotspot until you find where there's no contamination. So now we have A, B, C, and D. A, as before, above 10,000. B and C, between 10,000, and D, below 1,000. So on that, you would excavate, again, the hazardous as the pink, non-hazardous as the blue, and you can see it's come down quite a bit. 34 hazardous loads, 41 non-haz. And still all the contamination removed. We can actually do remediation real time. So we fill in the gaps of where there's some uncertainty. So instead of a 12.5 meter grid, we can down to even tighter than that. And you can see those spots where it's red and the ones which are green where we're not particularly bothered. And again, this is the amount of material taken out. The pink has, blue non-has. And that works out as 53 loads, 19 hazardous, 34 non-hazardous. Put that into context. The cost there are 44,470 using the site methodology to manage the entire site versus 241,932 if you were managing it using the standard wide grid. And 25 meters by 25 meters is actually not that uncommon. In fact, that's quite generous for a lot of sampling grids that I have certainly seen. And so it does make a big difference. You know, that is a huge difference. And remember, that is only at the a relatively shallow surface. Contamination extends several meters below ground, and so you can imagine those costs would have gone up had you stuck to the standard sampling grid methodology. And using iterative sampling will work to give you your 3D as well. So that just puts on-site into context as to how much it can save. So what are the ideal features of an on-site method? It's got to be easy to use. It's got to be simple to use, preferably by somebody who's not really qualified in the subject. It's got to be low cost. It's got to be accurate. That's equivalent quality to a laboratory, which some people might say, well, you can't do that with on-site analysis. Well, wait and see, shall we? Could be low failure or breakdown rates, and it's got to be robust. It's got to be readily available. So I'll give you a quick example here. This is the data output from an on-site analyzer called a QED HC1. So you can see here you get total BTEX, total GRO, total DRO, which gives you TPH, total aromatics, that's the C10 to C35 total aromatics, some of the 16 EPAs, which are actually the C10 to about C22 aromatics, and benzoate-pyrene. It also gives you potential carbon chain, so carbon number, proportions, and it gives you, and this is the most important thing, it gives you a hydrocarbon fingerprint match. And so you can see there it's showing degraded diesel, very degraded gas, petrol. We do a lot of work in America, and this is a British product, but because a lot of it is done in America, the software has been written from an American perspective. Now you can see there it's got a % confidence as well of the match. So the very top line, degraded diesel, FCM means in fundamental calibration mode. The P there means particulate present, and it's got a 72.4% confidence match that it really is degraded diesel. You can actually see though that the concentration is very low, so it doesn't really matter. But you can see further down, that's sample number 8 is showing 3,800 for TPH, degraded diesel with a 95.2% match. So all of that analysis, well, the BTEX, GRO, DRO, aromatics, all of that takes about 3 minutes per sample, and that 3 minutes includes sample preparation. And you get excellent correlation with standard lab methods. It's a very good QC procedure, and it's approved in the US as an alternative to method 8015. Method 8015 is the GCFID method that we typically use in the UK as well for TPH. This shows the fingerprints, because how does this instrument differentiate between the different hydrocarbon types? And you can see here there's a range of particular hydrocarbons, very different. So if you look on the right-hand column, third one down, you can see diesel. You can compare that to the one on the left, which is kerosene. You can see a very distinct difference. The conventional GCFID method does struggle to differentiate between these two compounds. And you can also see the top left is gasoline or petrol, again very different from diesel, but you can see there are some characteristics that are similarish to kerosene. It's all to do with fractionation of petroleum hydrocarbons using fuels. And that's what it looks like, set up in a bench, on a bench, so you don't need any facilities, and also you can see it running it under the back of the vehicle. I'll also just quickly touch on heavy metals, because the heavy metals and the hydrocarbons, you can do 90% of the analysis. So you can see heavy metals, you can get all the metals you want. It's under about 2 minutes per sample. You get an indication of homogeneity. So if the average value is green, it means that the 3 scanned results from that sample are very close. Yellow also pretty close, but oranges and reds does mean it's a bit more random. And that is true for heavy metals. They are usually not soluble, and they are usually unevenly dispersed throughout the soil, which is why having the averaging of 3 results gives you a much better accuracy and repeatability. So XRF does have excellent correlation with lab data when the instrument is used correctly, and they certainly have acceptable detection limits even for cadmium and mercury now. They're also a lot more robust than they used to be. You can actually drop them, but I wouldn't recommend it. So again, that's what they look like. So you can either use it as hand portable mode, or you can put it on a sort of a stand, as you can see in that bottom photograph, and you've got QED hydrocarbon analyzer right next to it. See, on-site analyzers don't take up much room, just a corner of a desk really. Right, I'm going to touch the elephant in the room, the regulatory approval of on-site methods, because you often hear the phrase, well, you're not allowed to use them. Well, actually, new MCERT's guidance was issued by Environment Agency back in August 2016 that endorses the value of rapid or on-site methods, and it actually encourages their use. And the actual wording does say that EA supports the uptake of new technology, including the application of in situ testing or rapid measurement techniques. They'll accept the results of in situ testing, but the results are complemented by a suitable MCERT's method. Now, there is no definition as to how many, what the ratio of on-site analysis samples versus MCERT samples are. It's variable, it depends on the project. Typically, a smallish project, it'll be 1 MCERT's result for 10 on-site results. But on the Crossrail project in London, over 14,000 samples were analysed by the on-site methods. That's the QED, XRF, and actually one for chlorinated solvents. And the EA were happy with just 66 66 samples of that 14,000 being sent off for confirmation with the MCERT lab. And that's basically because the results all came back in agreement. But the EA will take the entire data set into account, and they will use a lines of evidence approach when reaching a regulatory conclusion. And you may get a situation where you'll get all 10 on-site analysis results for hydrocarbons, say there's not a lot of hydrocarbon, but the MCERT result comes back and says there's lots. And so they're not really agreeing. But using a lines of evidence approach, you may discover actually that the on-site data shows there was background organic present and that the lab didn't actually clean up the sample. And in that case, the Environment Agency is likely to take the on-site analysis results as being the more accurate. So I'll come to that in a bit. But the Environment Agency recognised that the use of on-site analysis significantly improves the quality of a site investigation, i.e., as we've shown before, the more sampling points you have, the more likely your statistics is going to be good, and that can reduce the cost of both site investigation and remediation, as hopefully I have shown you already. So now we're going to go more onto the actual looking at this QED hydrocarbon analyzer and how it compares to conventional laboratory analysis. So, first slide here, what is the hydrocarbon? Now, normally I play a game with this one, so you'll just have to just make a mental note of this. What is the unknown sample? You've got reference A, reference standard B, and so which is it most similar to? I'll just try and make it a little easier. I'll now show you what those reference standards are. Now, the problem is with this lab, it's a GC method. So GCFE, the typical method that is used for petroleum hydrocarbon in this country. And this is the graphical output of the sample being sent down the GC column. And so unfortunately, different GC methods all use different columns, different conditions, different instruments, different standards, etc. So it is very difficult to compare the reference fingerprints or reference chromatograms with the sample unless they are all done at the same time. Now, this is an example where these two reference standards have been pushed down the column at the same time, so the same conditions as that unknown sample. So just bear in mind what you've all thought that unknown sample was. And now we'll go on to, let's look at using the QED hydrocarbon analyzer. Now there is the fingerprint that you get from the hydrocarbon analyzer. So you can compare that with the red line, which is the reference diesel. And this comes from a certified reference material. So that is what diesel looks like. And there's some similarities. It sort of fits at the front end, but not very well overall. That's what happens if you put a degraded fuel, certified reference material. That's a much closer match. So would it be a degraded fuel? Well, actually, if you use the certified Creosote standard, then you see that that's a very close match indeed. And basically, the fingerprint, as I said, is from a standard Creosote. It's the best match. Basically, the sample smelled of creosote, and it came from a Creosote works. Now, on site, you have the benefit of being able to smell what the sample is like. In this case, the laboratory didn't have the benefit of smelling that sample, and they identified the hydrocarbon as a degraded diesel, which is a bit unfortunate because they were wrong. So don't feel bad if you thought it was diesel. Even the professionals got it wrong, or the alleged professionals got it wrong. And that has some big implications because the material was disposed of as non-hazardous when in fact it was hazardous. And luckily, that didn't happen after April 2018, because everyone involved had been really hammered with some huge costs. As it was, it cost a particular company just over $1 million to get all of that sorted out. Here's another little experiment that was done. Some duplicate samples were made up, so a sand and gravel mixture was made up and spiked with 5,000 milligrams of diesel, and a sand and peat duplicate was made up. And these samples were packaged up, put into cool boxes with ice, and sent off overnight to 4 different MCerts accredited laboratories in the UK, and also to a laboratory, well, actually the QROS laboratory running a QED. We weren't told what was in, no one was told what was in the sample. It was just up to everyone to work it all out. And 2 of the labs were able to identify the sample as diesel, and the QED was actually able to identify it as undegraded red. Now, you can see that the values are significantly lower than the 5,000 milligrams per kilogram that everyone was expecting, apart from where there's peat present. This was a bit of a puzzle, but actually on receiving the samples, you opened up the cool box and you're almost knocked over by the smell of diesel. So that indicated that there'd been a lot of loss of volatile material. So we decided that that wasn't a particularly good way of doing things. So we repeated the experiment. When I say we, this was a third party, repeated the experiment using 75% weathered diesel. And 75% weathered diesel is where you basically get your fresh diesel and pass air through it and heat it up until 75% of the original volume has gone. And that should drive away all the volatiles. And you can see again that there is not quite as much as you're expecting, or we were expecting. There's actually quite a lot of variability between the labs as well, and that was also quite surprising. But the only thing that was consistent is that the labs routinely had much higher values for diesel or for TPH with the peat-containing material compared to just the non-peat material. And again, the QED not showing much variation at all. So you can see there that the results from the QED pretty consistent across all 4 samples. This is from one of the labs, and you can see there's quite a significant difference. It's pretty much double. And if you look at some of the other results for the MCerts Lab 4, 1,970 versus 3,951. Now these are duplicates, they're identical, so there is quite a wide variation. In fact, that exceeds the MCerts variability. So they couldn't really claim that that was within the accredited range. But we're still puzzled by the low levels, so the whole experiment was repeated again, but this time 5 minutes after spiking, the QED was used to analyze the samples, and yeah, this time you get near enough 5,000 milligrams per kilogram. I mean, I'm quite happy with those results. And then we packaged everything else, packaged it up again, shipped it overnight in the cool box with ice packs. Back down to my lab, so it had overnight, and the levels have dropped down again, 36% loss of hydrocarbon. And so that rather indicates that even shipping overnight in ice packs, you do see significant losses of hydrocarbon. Now, this could be because it was a sand and gravel mixture, so that's not particularly absorbative, but other soils may not lose quite as much, but certainly with sandy gravels, you are going to see quite a significant loss. Now, background organics. Rotted leaves, grass, and wood, they produce humic and fulvic acids. And those compounds are readily detected by the GCFID method as TPH. I think most people know that. But sample cleanup is essential to remove these interfering compounds. But the laboratories don't routinely perform effective cleanup. as you could have seen by those previous correlation studies. The QED is actually unaffected by background organics, but it can see them, it can recognize that they're there. So let's have a look at this slide here, which is a QED fingerprint showing the black line, which is the sample fingerprint. The red line is the reference diesel, so that's match, which is quite a close match. The first main peak matches, and that second peak is also fairly close. And if you look carefully, there's a sort of a yellow line there, and that yellow line is the residual left after the diesel has been removed, and a blue line is now following that yellow line. And that blue line is for a compound called bituminous. If you look up on the top left-hand corner, the first one is diesel, the second one is bituminous. Bituminous is basically petroleum hydrocarbon that's got degraded as much as it's going to get degraded. And so it's a very degraded hydrocarbon. So that's really just to show that that's how the system sort of works. The purple line is residual after that, and the system tries to work out what that might be. But in this case, it's not a formulated petroleum hydrocarbon that's recognized. So it'll just do some maths and work out what that residue is based on first principles. But yes, that extreme right-hand side of the fingerprint, you'll see a little lump. Here it is, and that is chlorophyll, which is a good indicator of background organics. So if that's present, you'll usually get a much higher value coming from the laboratory if they haven't done proper cleanup. And so going back to that original study, you can see that without proper cleanup, that peat is adding between 3,500 to 6,000 milligrams per kilogram of fake TPH. Now, if that was sand, just pure sand, or any soil with that amount of peat in there, automatically the lab results would have actually pushed that into the hazardous category under WM3, and you'd have been disposing of that as very expensive stuff to dispose of, when in fact it is unnecessary to. It is not TPH. So that puts things a little into context. You must get the labs to do proper sample cleanup, and having just one run of sample cleanup is not good enough. You often have to run 2, 3, or even 4 passes to get effective cleanup. Now, the problem with that, of course, is that each pass is actual analysis. So even if your lab is charging you £30 a sample, by the time you've done 4 passes through, you're up to £120 a sample. There is no such thing as cheap, proper laboratory analysis. Another one that crops up was a new one, RPS 211, utilities arisings. And utilities arising often contain road binder, because that's what holds the road together. And road binder made before 1980 often contained coal tar. And the coal tar came from the manufactured gas plants, which only shut down in 1975. And gas plants have been open since about 1775. So there has been an awful lot of coal tar kicking around. 200 years worth of coal tar kicking around, and someone discovered that it's really quite good to make road binder. The trouble is, coal tar is an absolute hazardous material under WM3. So anything that's got coal tar in is hazardous. Now, modern road binder is made from bitumen, which is the residue left from crude oil distillation. And bitumen found in road binder isn't hazardous. The problem is that bitumen and coal tar contain the same toxic compounds, the PAHs, but in different proportions. So this does pose a problem when it comes to doing analysis, because it's like trying to go into Tesco's and identify, in your carrot department, did the carrot, you take 2 carrots out, one in one hand, one in the other, do they both come from the same farm, or do they come from different farms? How can you tell? It's pretty difficult to tell. But it can be done, but it does require some very expensive analysis. You need GCFID on the extract for the print. You need GCMS on the extract for the target 16 polyaromatic hydrocarbons. You also need GCMS at certain alkylated PAHs. Those are the polyaromatic hydrocarbons that have got chains attached to them. And where those chains are and how long they are is actually key for identifying the difference between bitumens and coal tars. Also within coal tars you'll find X, and you can do that again, GCMS, specialized GCFID or HPLC. But put all those analyses together, plus the interpretation, and you're looking at between 150 and 200 pounds per sample using the conventional lab method. And if you do spend that amount of money, they always get the right result. Yeah, they are good when they want to be. So let's see how the QED addresses this particular issue. So here is a fingerprint, or two fingerprints rather, one of undegraded bituminous road tar. So that's fresh modern road tar, that's what it looks like. And compare that with, again, bituminous road tar, but it's now become very degraded. Right? This is what happens to it. Is when it's exposed to sunlight, rain, frost, snow, stuff being spilled all over it, and general wear, it changes, and that's what it looks like. So you can see there is a significant difference. However, let's look at 1950s road tar, and that's made of coal tar, and you can see it is quite a significant difference. And you also get mixtures, where you get standard bitumen-based road tars mixed with coal tar, and here you can see a fingerprint at the bottom showing bitumen with 13% coal tar in it. The confidence of that particular value is 84%. The confidence it's coal tar and the one above is 91%. So the QED is able to actually identify very quickly the proportion of coal tar in any road planings or utility arising from the binder. And this sort of gives an indication of how it does it. So there's a fingerprint, the top one's the black line on that top fingerprint. You can see the red line of the first match, which is the bituminous material. And this bituminous material comes from, our reference standard comes from a certified reference material of raw bitumen. It subsequently goes in to make road tar, or the bitumen road tar. And the blue line underneath is the formulated standard road tar material, and you can see that that is the closest match. That's why this sample is identified as standard bituminous-based road tar. The fingerprint on the bottom, though, that is again showing the bitumen as the first match, but the second blue line shows a coal tar. And there's those distinctive peaks of coal tar present. And so it's identified this as a material that contains a certain percentage of coal tar. It's not pure coal tar, but it has got some in there. And so therefore, under WM3, that is potentially hazardous. So basically, this is the report that the QED would generate. And because it's using, it's doing the road binder analysis, you can see there that if it identifies degraded bituminous road binder, you don't find much benzoate-pyrene. But as soon as you find some coal tar in there, the system then works out what is the percentage of benzoate-pyrene in that coal tar. In this case, 0.278%, which is above the 0.005% that is within the regulations of WM3. So typically, if you have more than 0.1% coal tar in your bitumen-containing material, it's hazardous. But you can use benzoate-pyrene as a marker, and if it's below 0.005%, you can classify it as non-hazardous. But if it's got coal tar in it, it's unlikely to go below 0.005%. So that's how the QED can do it. Basically, it'll do it in less than 2 minutes. That's including the sample prep. It is accurate. There's plenty of correlation data now from labs that have done the £200 per sample analysis. It's very simple. Anyone can follow it. It really is that simple. Costs as little as £5 per sample and can be carried out on site to give immediate information. So when we start now looking at the new rules under incorrectly classifying your waste and the new rules with RPS 211, I do feel sorry for anyone who's digging holes in the road, because as soon as you've dug through the road surface, you're now effectively got to classify that material as hazardous unless you can prove otherwise, which means you need to then take it to a site that is licensed to take hazardous material. There aren't many of those around. So all of a sudden the cost of digging holes in the road goes through the roof, unless you start using the QED to give you very rapid analysis data, so you'll know exactly what the hazard classification is. Because at the end of the day, with utilities arising, the vast majority of the time, the reason it is classified as hazardous is because of the coal tar in the road binder. So let's just, which is best then, on-site or lab analysis? Well, back in September 2017, the Environmental Industries Commission, Laboratories Working Group, found they could not recommend the current lab method for TPH using GCFID for inclusion into something called the Analyst Blue Book. And this was due to the inherent variability in the method. So their own internal discussions, basically it was about a ×5 variability. But the same sample sent in could be as much as ×5 difference in the concentration reported, which really isn't that acceptable. In the US, where they do have facilities for verifying and validating alternative methods, the US Department of Transportation recommend the QED TPH method over the GCFID method. And so that really is indicating that on-site analysis is becoming as good, if not better, than the standard lab methods we have been using up until now. However, I'm not trying to knock lab analysis, far from it. We all need it, but we need good quality lab analysis. And good quality lab analysis is brilliant for your high resolution individual target compound analysis. You're using good quality GCMS. Okay, and you need this for creating risk assessment models. But because it takes weeks to get a result, it's really only suitable for site investigation. To do it properly, it's going to be expensive. If you go to a restaurant, you can go to a Michelin-starred restaurant, it's going to be good food. Or you can go to McDonald's, which isn't. There is a price differential. You get what you pay for. But if you know what samples you can send to the lab, so using on-site analysis, you can select the appropriate sample to send for the expensive analysis, and then you get the data you need. And when it comes to remediation, all you need are a few samples, and that will verify you, because you'll know that from the on-site data that you're going to get the answer you're expecting. So, latest generation of on-site analyzers, they do give high quality with low sample costs. There are CSM. You can, as I said before, select the right samples for being sent off, and it is very good for SI remediation or WM3 classification. So I will leave you with some further reading for you to ponder on. The last bit I will say is that these analyzers, these on-site analyzers, if you mount them in a laboratory, a fixed laboratory, you can get UKAS or MCERTS accreditation for them. Unfortunately, once they become accredited, then you decide to take them out on site or move them even half a mile down the road, they are no longer accredited. And this is the problem with the current accreditation system for chemical analysis in this country. It's broken. It doesn't work. But there are some labs now putting these analyzers into their labs and looking to put them through UKAS, or they are putting them through UKAS. So you may find that these methods can come with UKAS accreditation, but if you use them on site, they're not. We are trying to get that sorted out. But there we go. I think that is the end of my presentation. I hope you all heard me, that I wasn't talking to myself. And I will answer questions as they come up. And I see some have come through from Marianne. Can you download the raw data from the QED? Yes, you can. It comes out as an Excel file. Detection limits. The lowest detection limit for the QED, or the lowest concentration calibrator, what we use for quantification, is 5 parts per billion. The actual detection limit for most of the PAHs is 100 parts per trillion. Pretty impressive for a tiny little box. But these things that basically both the QED with that method and the XRF for heavy metals, they're used on the space probes. They're wandering around Mars. They went to a comet, I think, this summer, going off to have a look at Mercury as well. So it's all space age technology. So they are very, very good. So if anyone has any other questions or anything, if Rhiannon's there.
Yep. Yeah, I was just waiting for you to finish that one. Thank you, Colin. That was a very detailed insight into what seems to be a very sophisticated system. So thank you for that. Yeah, like I said, you've answered Marianne's question already, which is brilliant. If people do have any further detail that they want from you and further questions, is it yourself that they contact, or who's the best contact to come to at QROS?
They can come to me, or just info at QROS, or Colin at QROS, or go to our website and there is a free phone number. I think it's press 1 or 2. I think I'm on 2, so because I'm more technical.
Okay. Okay, perfect. So I'm sure there'll be others that will come through with questions once they've kind of digested that in a little bit more detail. Amy, yes, the presentation will be made available on our YouTube channel once Colin and I have just confirmed the content. So yes, you can go back to some of these slides on there at a later date as a useful resource. But yeah, that is the majority of the questions that have come in. So thank you, Colin. That was really detailed.
It wasn't that boring, was it? Come along, guys. I'd have thought a few more questions.
Not at all. Not at all. I think it's just an element of people needing to process that and working how they can actually apply that to their day-to-day. So we might get some more questions in. If I do, I can send them over to you. But in the meantime, thank you to all the attendees that have logged in. Make sure you record this as CPD on the CPD tool. You can find all that information on the IES website, and if you've got any problems, do contact the project office so we can help you out with that. Our next webinar will actually be in January now, in the new year, which will be looking at streamlined energy and carbon reporting. We've got 2 presenters from WSP presenting on that, both James Capson and George Baker. We'll look at that in the new year. Registration for that will be up at the end of the week, so do take note of how you can apply and attend for that webinar. So unless there are other questions coming in, just thank you to Colin for your time and for giving that presentation. And yes, like I say, it will be made available on our YouTube channel for those to catch up and share with their colleagues who missed it. So thank you, Colin.
Okay, pleasure. Thank you for listening, folks.